Good day, stats students. Today we're going to go over part 2 of section 3.3. Specifically, we're going to go over R squared. So R squared, another name for it is the coefficient of determination. R squared is good enough for this class, but if it's ever brought up at another class and they use the real wording, there you go. All right, what is it? It's the percentage of variation in Y that is explained by having X in the regression model. So there's a certain amount of variation in Y, and we want to explain that variation. That's all. And how good is X at explaining that variation? Okay, and that's what basically R squared is. Now it is true that you can simply take R, the correlation coefficient, and simply square it, but that's just to get the calculation. Okay, we're going to talk more about how to calculate this in a more sophisticated way here in a little bit. R squared is a number between 0% and 100%. Now in StatCrunch, you're going to see it as a decimal, all right? And so probably it should be shown as a percentage. It's fine, you know, um, but it's usually thought of something between 0% and 100%. And like I said, we're going to look at how to calculate R squared in a different way than just simply taking R and squaring it. Okay. Um, so as you can imagine, that we want to explain more of the variation. So something for R squared that is closer to 100% than 0% is better. That's telling us that our model is pretty good. X is pretty good at explaining Y. Okay. So R squared, in the classical definition here, since it's the percentage of variation that in Y that is being explained by X, that means that it's a fraction. It's the numerator would be the variation in Y that's explained by X divided by the total variation in Y. And that we have names for those things: SSR and SST. SSR meaning sum of squares for regression. We talked about sum of squares before when we talked about SSE. And we're going to see SSE again, all right, later on in this video. But for right now, the numerator is SSR and the denominator is SST, sum of squares for total. Total what? Total variation in Y, all right? And so let's go ahead and try to figure out, well, what exactly is SSR and SST? SST is pretty easy, all right? Let's start with that. What's the total variation in Y? Well, remember this. This is the variance formula. It's just that it's applied to X. Well, let's apply this formula to Y, okay? And so we'll apply it to Y, and this is what you get, okay? And so SST is just the numerator of that thing, okay? So the numerator of the variance is the sum of squares for total variation in that variable. Once you divide it by n minus 1, you get the variance, and then you take the square root of it, you get the standard deviation. All right, so that's all that SST is yi. So each one of the values of y, subtracting off y bar. All right, we can't just sum it, because if we just summed it, it would turn out to be 0. So what do? We got to square this stuff so we don't have these compensating net positives and negatives. Okay, so there you go. There's SST. All right, SSR is a little bit more involved. Okay, so the best way to explain this is with a scatter plot. And that's what we're going to do here. All right. So here's a scatter plot. We haven't worked with this data. I just put 10 observations in there, both with an X and a Y, obviously, because we're talking about regression analysis. And I just put it into StatCrunch, had it create the scatter plot for me. Okay. And what we're going to do here is that we're just going to go ahead and, oh, I put in Y bar. We're going to need that. So there's the line for Y bar. And what we're going to do is we're just going to focus in on that value up there. Okay, just that one. So we're going to get rid of all the other ones. There, all the other ones are gone. And let's just focus on this one for right now. All right. And so notice here that if we, here, remember, SST again is yi minus y bar. So that means that if we looked at the value of y for this observation, subtracted off y bar, all right, we would start to calculate SST. And so if you think about it then, that would be just the distance from that point of y down to y bar, that distance there, okay? Because remember, we're talking about in terms of y, not x. So in terms of y, it's vertical, not horizontal, all right? And so um, let's just pretend, I know it's not sitting exactly at 5, but let's pretend that y bar is sitting at 5, okay? And the value of y for this observation is 10. And so we're talking about, 10 minus 5. That's all we're talking about, right? 5. And so we're just talking about that total distance there. So this would be the start of calculating SST. Okay, so this is this observation's contribution to SST. So we can break it up in the distance into two parts. Okay, here's the first one. So we're breaking up the distance for SST into two parts. The first one is the residual. How much did we miss by? We talked about that quite a bit in 3.2. Okay, so there's your residual. Okay, and I'll remind you of something. Okay, so remember when we talked about SSC, that's coming up. Okay, sum of squares for error. Remember error and residual. Okay, all right, then we have this distance here. Okay, so it's the value of y hat on that line down to y bar. Okay, and let's read what it says here. How much of the variation y that is being explained by x for this particular observation? Okay, that's how much of the variation is being explained by x for this particular observation. Okay, so we got these three distances here again. So we got we got this distance here. That's the contributions towards SST. We got this distance here. This would be the contributions towards SSE. There's your residual. And here's the improvement. Here's the improvement. Okay. Why is it an improvement? Because notice our red line, our least squares regression line, is closer to the dot than y bar was. Okay. And so notice we have an improvement there. Okay. And so we're explaining some of the variation. Right. And so SST, so this observation's contribution towards SST, SSE, and this would be SSR, okay, the contributions to SSR. And so there's your three distances there. Now, here's the thing, is that we wouldn't just do that for that observation, okay? We would have to do that for each one of these observations. Literally, we would have to figure out y minus y bar, not just for that observation, but for all 10 of our observations. We would have to then figure out the residual. Then we would have to figure out how much of an improvement did we have, so from the line down to y bar. And we would have to do that for each one of those to calculate SSR. So it's kind of involved, okay? So we're not going to do that by hand, okay? But it's good to hear the explanation of what's going on here. So here's the thing, is that if you did any one of these calculations, and we've kind of already talked about a lot of this before, is that if you start just summing up stuff like this, especially that involves y bar, but even the middle one, y i's minus the y hats, if you sum that up, it comes out to 0. So that's pretty useless. So what do? We square things out to get rid of the compensating negatives and positives, okay? And so that's where SST comes into play. Sum of squares, okay? We're squaring stuff, all right? And to get rid of the corresponding positives and negatives, okay? Here's SSE, and then here is SSR. So the y hats minus the y bars, okay? Squared, and there you go. And you sum them all up, okay? And so there's SSR, all right? And so it's the improvement that we're seeing here in our model, okay? And how much of the variation in y is being explained by throwing x into the model. Simple as that, okay? So there's your numerator, there's your denominator, okay? And the more that is explained by x, the higher r squared will be, giving us a indication that, hey, we got a pretty good model, okay? As long as we're, closer to 100%, right? Okay, so remember this, remember we worked with this back in, I don't know, either 3.2 or 3.3 or something like that, the beginning of 3.3 anyways. Here's R. So we know for our small little data set that we were working with, we know that it turned out to be a negative 0.9. Okay, so if we went ahead and squared that, we know it should come out to 0.81. Okay, so keep that in mind. All right, keep that in mind because we know that R squared should turn out to be 0.81. All right, now before I show you some stuff in StatCrunch, I just want to point a couple of things out. Here would be the interpretation. This is important then. So 81% of the variation of y is explained by x. This is good. It's explaining a lot of the variation. So R squared is one way, but not the only way to assess how good your model is. Okay, and we kind of already talked about this. Closer that we are to 1 or 100%, the better. Okay, but this is not the only. There's a bit of a caveat to R squared, which we're going to talk about in Intro 2. Okay, I'm going to kind of leave that for Intro 2, but there's you can't just look at R squared by itself. Okay, let's see. Will be displayed in any regression computer output. Okay, so I'm going to show you StatCrunch. Now, by the way, you can also use this to compare different models. So if you have, if you're trying to explain y, and you have two different x's, okay, and you put them in two different models, you can start comparing the models. How well did one model compare to another one? The one, generally speaking, the one with the higher R squared is doing a better job, okay, of explaining why. So what I'm going to do here is I'm going to hop out of this and I'm going to go over to StatCrunch. So I put our data in here that we've been working with in either online or in class, whatever, depending on how, when you're taking this course. And what I'm going to do here is I'm going to go to Stat. I'm going to go down to Regression, Simple, Linear, put it in our X, put it in our Y, and hit Compute. There we go. Let me take this, bring it up, and I'm going to expand this. And you're going to have to do this when you run the regression, is that I would expand it a little bit. Okay, a couple of things. Here's R. We knew that it was a negative 0.9. And there's R squared, 0.81, all right, or 81%. Okay. Now, that's not the only thing I want to bring up to you guys. The other thing I want to bring up to you is down here, this analysis of variance table. This is where you find SSR, SSE, and SST. So it says model here, okay? But if you kind of combine these, this idea here that it's generically what we call for regression here. So if you kind of combine that idea there, this number right here is SSR, okay? So the 32.4, the SSE is a 7.6, and the SST is 40. So here's your numerator for R squared of 32.4. If you divide it by the denominator of 40, guess what you get? You get that 0.81 or 81%. So here is a scatter plot, okay? And just, I can't really do this, but I can kind of temporarily draw Y bar in here. So here's Y bar, okay? It's right at 4, okay? Now it's going to go away, but that's okay. So just imagine that, that we just looked at this observation here. So if you went from 8 down to 4, okay, there's SST. Here's your residual. It's a very small residual right here. That would be the residual, that distance there from that point down to the line. And then what's left? From the line down to Y bar, there's your improvement. So look how much of the variation is explained with that for that one observation. Okay, so the closer the line is to the dot, there's just a little bit of contribution towards SSE, very small residual, and a lot is being explained as far as the variation goes. Okay, and so so I want you to think of this for a second. Remember, I told you that when we create our one best line, we are minimizing SSE. That means if SSE is being minimized, what's being maximized then? And that would be SSR. Okay, so that's kind of the other reason why We chose the line that we did because this maximizes SSR, it minimizes SST, excuse me, SSE. I said that wrong. It minimizes SSE, okay? And it basically does its best in calculating basically your highest R squared that you possibly can for our, one best line, okay, to fit our data, okay? So there you go. So R squared, all right? Well, thank you for your time. That's what I had for you today.